This section explains how a pKa value can be reached by computation instead of by titration. A titration number becomes a computed number. pK is an aqueous observable, and the chapter's whole move is to reach it without wet chemistry. The method decomposes the free energy of protonation in solution divided by 2.303 times RT times RT point T-nation through a thermodynamic cycle into a gas phase term computed directly from the electronic structure using density function correction supplied by a PCM continuum. That free energy then maps linearly. The generative primitive is this. A solution phase quantity is reconstructed as gas phase energetics plus a solvation. Delta. One calibration point buys the rest. Methylamine fixes the basis set, the 6311++ GDP set, at 0.4% deviation against experiment before the remaining 14 amines are predicted. Trust is earned on a known point, then spent on unknowns. This section explains how a measured acid-base constant becomes a computed number. The primitive is this. pKa is a deprotonation free energy in disguise. The negative logarithm of the acid dissociation constant equals the change in free energy divided by R times T times the natural logarithm of 10. That single identity is what lets a wet lab equilibrium constant be reached by calculation. The generative move is a thermodynamic cycle. You never simulate the aqueous reaction directly because that is intractable. Instead, you route it through gas phase proton chemistry, meaning basicity and proton affinity, which are cheap and clean under density, functional theory at the B3LYP level. Then you add a solvation correction, the IEFP-CM continuum model, which drops each species into implicit water. Sum the legs of the cycle, and the awkward solution phase quantity falls out. The alkylamine series is the anchor. Predicted pKa climbs with carbon count and tracks experiment. The lesson generalizes past amines. Any solution property that has a gas phase, analog, plus a solvation patch is computable this way. The cycle is the primitive, and the molecule is incidental. This part explains how a computational chemistry chapter turns reactivity into something you calculate rather than something you watch happen. Reactivity here stops being something you observe and becomes something you cons or is attacked. The reaction never runs. Number. Fix a molecule's ground state electron density with DFT, and every reactive tendency falls out as a functional of it. The global descriptors, hardness, electrophilicity, and electronegativity come from the frontier orbital energies. The local ones, the Fukui functions, pinpoint. The chapter's move is a controlled ablation. Take coumarin's 1-alpha-beta double bond and saturate it into 3,4-dihydrocoumarine. Then watch the descriptor shift and attribute the whole change to that conjugation alone. Substituents and hydroxyls are further single variable twists on the same knob. Its place in the book is to be the exemplar. The path from structure to reactivity is a calculation, a thing computed at a desk rather than measured at a bench. This section explains how a structural edit to a molecule turns into a reactivity prediction with no measurement in the loop. Reactivity here is never measured. It is read off the ground state electron density, which DFT treats as the sufficient statistic for the whole molecule. The chapter's move is this. Take coumarin, delete its alpha-beta carbon double bond to reach the metabolite dihydrocoumarin, and let the difference in the density-derived descriptors isolate exactly what that one conjugation channel contributes. Those descriptors are the Fukui functions, the HOMO-LUMO gap, the electrophilicity, and the HOMO-LUMO gap, the electrophilicity, and the hardness. Each hydroxy substituent is the same experiment rerun. It is a controlled perturbation of the same density, its donor or acceptor effect quantified by NBO. The primitive you keep is this. A structural edit becomes a reactivity prediction the moment you can name which region of the electron density it reshapes with no wet lab in the loop. This section explains how phosphorylation controls whether FKBP12 recognizes the TRPC6 channel and where that recognition actually lives. Phosphorylation is a switch that manufactures a charge, and recognition follows the charge. FKB-P12 ignores the bare TRPC6 peptide, phosphorylate. Serine 768 and the new phosphate reaches two lysines, lysine 44 and lysine 47, waiting in the binding pocket, and the complex loxing, waiting in the binding pocket, and lysine 47, waiting in the binding pocket. The chapter's move is that molecular dynamics with molecular mechanics generalized, Born surface area free, energy decomposition attributes this whole affinity to named residues. Binding is a property of one salt bridge pair, carried by that single contact rather than by the peptide as a whole. Swapping phosphoserine for aspartate or glutamate tests whether charge alone suffosidate or glutamate tests whether charge alone suffices. The primitive specificity is switchable. Electrostatic complementarity and computation can localize it down to the single contact that carries it. Recognition acts as a switch, and the switch is one phosphate. FKBP12 barely holds the TRPC6 peptide until serine 768 is phosphorylated. Then the phosphate clamps onto lysine 44 and lysine 47, and the complex turns favorable. The chapter's move, the primitive worth-keeping, is that binding affinity, one global number, gets decomposed onto individual residues by mmgb/SA over explicit solvent dynamics. The computation does not merely score the complex, it names which atoms carry the energy. You locate a switch by attributing a scalar to its parts. The aspartate and glutamate mutants close the argument. They mimic the charge, they recover the binding, and so recognition reads electrostatics, not the particular residue. This section explains how the design of PDHK inhibitors follows from the shape of the target rather than from the chemistry of any one drug. The object to design is the complement of the target. PDHK2 offers two pockets, and each pocket's chemistry is itself the search program. The orthosteric site binds charged pyruvate and dichloroacetate through hydrogen bonds, so you screen small, polar, donor-rich molecules. That charge polarization forces quantum treatment exactly where classical force fields misreport bond lengths. The allosteric site is a deep lipophilic groove, the coenzyme A, analog called PFZ3. There you grow larger ligands and swap hydrogens for fluorine, because fluorine raises hydrophobicity, filling grease with grease. The tidal span, from small molecules to large fluorinated compounds, records a change of pocket. The ambition stays constant. Complementarity is the invariant, and each site's polarity already fixes the ligand scale and chemistry before any screen runs. This section explains how a known drug design problem was solved by starting from nature's own regulatory chemistry. Nature already solved the binding problem. Pyruvate and coenzyme A inhibit PDHK because they are its regulatory ligands, so the design task starts from a known good seed rather than a blank slate. Cocker's chapter is the book's demonstration that computational chemistry can walk chemical space uphill. Take the crystallized DCA and PD, HK2, complex, characterize the site, then let a cheap surrogate, a docking score standing in for the wet lab assay, rank homologous molecules. An ADME and Lipinski filter bounds the search to what a body tolerates. Small molecules give way to the larger fluorinated PFZ3 analogs as the score climbs. The generative primitive is this. Swap the expensive fitness evaluation for a computable one, seed from nature's solution, and let druggability constrain the walk. This section states the chapter's central claim that molecular modeling's real limit has moved and what you must rebuild once it does. The bottleneck migrated. Molecular modeling's limit stopped being raw compute. Serial Moore's law died into many core, and no toolbox upgrade converts the accelerating flood of researchers, problems, and accumulated data into actual knowledge. The chapter's thesis is this. When a field's binding constraint moves from computation to integration, you rebuild the substrate itself, rather than upgrading the tools. A cyber infrastructure fuses compute centers, curated data repositories, digital libraries, high-speed networks, and people into one composable fabric. So multi-scale methods that span orders of magnitude in space and time, the Karplus, Levitt, and Warshall move close under a single framework. The surprise the authors press is that the change is cultural, reaching all the way to how research itself is conducted. It is Hay's fourth paradigm, data-intensive science. A new toolbox never reaches that far. This part explains how the bottleneck in molecular science moved. Once Moore's law stopped buying single core speed and began spreading transistors across cores, the scarce resource stopped being the number-crunching engine. It became the fabric that binds engines, data, graphics, networks, and people into one workflow. That fabric is the cyber infrastructure, and SMART is one workflow. The move that makes the chapter go through is multi-scale. Each method holds only within one window of space and time. Quantum methods for atoms, classical methods for thousands of atoms, continuum methods above that. No single one spans the range a real phenomenon occupies. Integration composes them into a unified description across orders of magnitude. The chapter's thesis follows. Scientific productivity now scales with connective tissue, not with raw compute. This section explains how computational chemistry turns dye design into a search problem. Design becomes search when the map from structure to property is cheap to evaluate. That is the whole chapter. Quantum mechanical calculation, density functional theory, DFT, together with its time-dependent form, TDDFT, turns structure, determines function into a computable forward map. So a die is optimized into a computable forward map. So a die is optimized in silico before Renyi synthesis. The target property is a red-shifted absorption, that is, a narrowed HOMO-LUMO gap. It is steered by editing one fragment of the modular d-pi-a die, the donor, the pi bridge, and the acceptor. The step that does the work is calibration. The model is first tuned against a reference die whose behavior is measured, TA Saint CA, at 9.1% efficiency. Only the model that reproduces the known is trusted on the unknown. Prediction replaces the synthesis bottleneck, but only within the reach of the anchor that validated it. This section explains rational die design as an inversion of the usual structure to function map. Structure determines function is the forward map. Rational design runs it backwards. You fix the target first, pushing the die's absorption edge toward the infrared, which means shrinking the HOMO-LUMO gap. Then you perturb a structure until the simulator predicts that target. The donor, pi bridge, acceptor skeleton is what makes the inverse tractable. Donor, pi bridge, and acceptor are near-independent knobs, so the search over structure space factors into per fragment moves. The whole method rests on one move, calibration. A DFT model earns trust only by reproducing a measured reference die, TASTCA. After that, its predictions on unsynthesized dies are believable. Synthesis stops being the search and becomes confirmation of a search already won in silico. That inversion, where the property specifies the structure, is what the chapter is for. This section explains why the whole physics of an organic molecule on a metal collapses onto a single number and how the chapter recovers that number from first principles. A molecule resting on a metal becomes one number, the offset between the metal's Fermi level and the molecule's HOMO and LUMO. That offset gates charge injection, so the entire device performance collapses onto orbital alignment at the interface, and alignment is fixed once you know where the molecule sits. Hence, the chapters move. Use first principles DFT for periodic solids to predict the stable adsorption geometry. Then read the electronics off it, the work function shift, the density of states, the Schottky barrier. Adsorption is always exothermic, and it splits cleanly by energy scale. Fissorption sits below -20 kilojoules per mole, a van der Waals interaction, distant. Chemisorption sits above -40 kilojoules per mole, a real bond, and it is monolayer limited. The pentacene on palladium-100 interface. Is the worked instance carrying the palladium-100 interface? Is the worked instance coring? This section explains why charge injection at an organic molecule and metal contact reduces to a single move, and why geometry must be solved before electronics. Charge injection across an organic molecule and metal contact is fixed almost entirely by where the metal's Fermi level lands relative to the molecule's HOMO and LUMO. So the whole chapter reduces to one arrow. Solve the adsorption geometry first, then read the electronic offsets it produces. First principles. DFT gives the stable configuration. That configuration is Fissorpted by van der Waals forces below roughly -20 kilojoules per mole, or chemisorbed through a real bond above -40 kilojoules per mole, and it can lie flat, sit tilted, or stand upright. That geometry then dictates the work function shift, the density of states, and the Schottky barrier height. The pentacene on palladium-100 interface is the worked anchor, the primitive that carries. An interface's electronic behavior is a function of its geometry, computed in that order, never guessed. This section explains why catalytic power in these small metal clusters lives at a single atom rather than in the cluster as a whole. Catalytic power here belongs to the individual binding site. A 4-atom palladium or platinum tetramer cracks methane's carbon-hydrogen bond, but the cluster's whole verdict, the barrier height, and whether the reaction runs exothermic or endothermic, is set by the one atom the methane lands on. A platinum site cleaves the bond downhill, and cheaply. Doping is a knob that retunes each site's frontier, orbital energetics locally. The palladium-platinum 3 cluster wins by presenting a single, maximally active platinum site. Platinum does not need to cover the whole surface. One good site decides the outcome. The generative move is this. Read the barrier off the local electronic environment of the binding atom, and the ranking of the bimetallic clusters follows without recomputing the whole surface. This section explains why methane's stubbornness is really a question about which single atom it meets. Methane's inertness is a single bond problem, one carbon-hydrogen bond has to break, so the whole catalytic question collapses onto which atom the molecule meets. Chapter 8's move is to read the reactivity of a 4-atom palladium platinum cluster off its active site, the one atom the molecule actually touches, rather than off a bulk average of the cluster. The numbers make the point sharp. Present methane a platinum atom, and the barrier is about 3 to 6 kilocalories per mole, exothermic. Present it palladium, and the barrier climbs past 25, endothermic. Same cluster, opposite verdict. Alloying works as a dial. Doping tunes which face the molecule adsorbs on, and the composition palladium platinum 3 with an exposed platinum site wins. The generative pattern to carry forward is that catalysis localizes. Composition matters only through the atom actually touched. This section explains how a single quantity fixes every electronic and optical property. The chapter reports for small copper-silver nanoalloy clusters. One scalar governs everything else, the HOMO-LUMO gap. Fix the 2 frontier orbital energies of a copper-silver cluster carrying n silver atoms, and every property, the chapter felicity, electrophileptical response, all fall out of that same pair. Those quantities are the ionization energy, which equals minus the HOMO orbital energy, and the electron affinity A, which equals minus the LUMO orbital energy, both read off by Koopman's theorem. Hardness, softness, electrophilicity, electronegativity, and even the qualitative optical response all fall out of that same pair. The chapter's move is compression. A whole experimental property table collapses onto 2 numbers that a single DFT run already gives you, with no optics measurement needed. The pattern that carries forward is odd, even oscillation. Even N clusters sit at wider gaps, so they are more stable and less reactive than their odd neighbors. Electron pairing buys rigidity. Predict the next cluster's behavior from its parity and its gap alone. This section explains how a single number, the HOMO-LUMO gap, generates a whole family of chemical reactivity descriptors. That one scalar, the gap between the highest occupied and lowest unoccupied molecular orbital, is treated as a generating function. Hardness is half the gap. Softness is its inverse. Electronegativity and electrophilicity fall out of the same 2 frontier energies through Koopman's. So this chapter's move is that you never measure optics or stability directly. The surprise that updates you is parity. An even atom count closes the electronic shell, widens the gap, and yields a less reactive cluster. The odd-even oscillation across the copper-silver clusters from 1 to 8 is downstream of a single integer. Underneath all of it sits pars dictum. To calculate a molecule is not to understand it. This section explains multisolitons in split ring, resonator metamaterials, and why their behavior follows from the equation. The lattice is built to obey. A split ring resonator array is an equation you already know, fabricated. Each ring is a nonlinear oscillator. Mutual inductance couples neighboring rings. The magneto-inductive wave running along the chain obeys the nonlinear Klein-Gordon equation, the same form that governs solitons in optical fiber and in DNA. So its excitations are genuine solitons, localized, shape-preserving, colliding without dissolving, particle-like. The chapter's move is design by equation. You fabricate the lattice, whose governing partial differential equation you want, and multi-solitons and discrete breathers then follow as guaranteed modes of that lattice, arriving by construction rather than by luck. The discreteness of the array is what turns the continuous soliton into an intrinsic, localized mode, and the soliton's substrate. Independence, fiber, molecule, metamaterial, all one equation, is the entire leverage. This section explains what a soliton is on a metamaterial lattice. A soliton is what a lattice does when spreading and steepening cancel exactly. Each split ring resonator is a nonlinear RLC oscillator. Wire them into a periodic array coupled by mutual inductance, write the Hamiltonian, and the field equation is the nonlinear Klein-Gordon equation. Lattice coupling disperses a pulse. The RLC nonlinearity sharpens it. At balance, the pulse locks into a shape-preserving packet that translates like a particle, riding the magneto-inductive wave. Multi-solitons are several such packets coexisting. The chapter's move is this. An engineered metamaterial becomes a field theory whose particle content is its own localized excitations. The boundary that reveals the structure is integrability, which decides delivery. Sign. Gordon hands you these solitons analytically. The non-integrable Klein Gordon equation here yields them only numerically. This section explains how all of light-matter interaction reduces to computing a single quantity, the total polarization, written PT. Maxwell's equations govern fields in vacuum. Drop matter in, and the entire response, dispersion, nonlinearity, quantum activity, enters only through PT, the term coupling D back to E. So light-matter interaction is the problem of computing one source term. The chapter is a ladder of ever richer PT. First, a linear dispersive permittivity, then a fully quantum active medium by way of the Maxwell block equations. FDTD earns the name ab initio by solving the real equations on a Yee grid, with no approximation, only discretization. The closing elegance is this. The many block equations collapse under SU of n symmetry, and matter's whole state is written as a single coherence vector. This part explains how the finite difference time domain method, FDTD, folds the entire optical response of a material into one quantity. Everything the medium does to light collapses into one term. Maxwell's equations are universal and material, blind, so the chapter's move is to route the entire physics of the material, its dispersion, its nonlinearity, its quantum activity through the total polarization, written PT, sitting in a single update equation. The solver never changes. That is why FDTD is ab initio, meaning no approximation to the field dynamics, while still modeling dyes or quantum dots. You swap the polarization model, not the algorithm. The Yee grid earns this by placing each field component inside its own curl, so the differential operators become local differences. Master the PT factorization, and every later material is just another closure. This section explains why adding more elements to an alloy can make it simpler rather than more brittle. Add a sixth element to an alloy and intuition predicts brittleness, a zoo of intermetallic compounds crystallizing out. The chapter rides the inversion, configurational entropy by simplicity. Free energy is delta H minus, competition, or SEC delta S. Pack 5 or more elements at mere equiatomic fractions and mixing entropy, climbing from 5.8 up to 15.0 as you go from a binary to a hexanary system, grows large enough to overpower the enthalpy that would order the atoms into compounds. So a single disordered solid solution, plain BCC or FC, composition stops naming a base. plus dopant hierarchy, it names a maximally mixed lattice held together by its own disorder. The next case follows: more equal species, more stabilizing entropy provided atomic sizes stay close enough. Here, delta equals 9.27 to forbid amorphous collapse. This part explains why 5 or more metals mixed in equal proportions freeze into one disordered phase. You would expect them to curdle into brittle intermetallic compounds. Instead, they settle into a single, random solid solution because configurational entropy wins. The reason lives in the Gibbs free energy. The mixing term is minus T times delta S of mixing, and that term scales with the number of components, since delta S of mixing equals R times the natural logarithm of N at equal molar fractions. So crowding 5 or 6 elements onto one lattice makes the disordered mixture the lowest free energy phase. Outcompeting every ordered arrangement, these out-competing every ordered arrangement. That is the whole generative move of a high-entropy alloy. Entropy is recruited as a structural stabilizer, and simplicity, one solid solution, emerges precisely because the mixing is maximally messy. The chapter's job in the book is to instantiate this. It synthesizes the alloy of aluminium, magnesium, iron, copper, chromium, and nickel by ball milling, then reads the entropy-favored body, centered cubic or face-centered cubic solid solution straight off an X-ray pattern.